Welcome back to the Professor's DuBois channel. Professor Victoria and Professor Corey here, and today we're going to start off a buffer series. So we're going to have a series of videos, and we're going to cover what a buffer is and how they work. We're going to go into calculating the pH of buffer solutions in a couple different ways, and we're going to talk about calculating the pH of buffer solutions before and after adding strong acids and bases, as well as how to make a buffer. And we're going to cover a couple different ways of being able to make a buffer solution. So we're going to get right into this first video.
So in this first video, we're really just going to talk about, what a buffer is and how it works. We're not going to do calculations in this first video. So if you're a little confused about what buffers are, this is where you want to be. If you're pretty comfortable with what a buffer is and how it works, you may want to just go forward to the next video in the series where we'll start doing some calculations. But by definition, a buffer will cause solutions to resist a change in pH when a small amount of acid or base is added. And I think the misconception here is that a buffer can actually hold a pH constant, and it cannot. But if we add a small amount of acid, the pH won't change much. It will change a little, and adding acid will cause the pH to decrease, become more acidic. Adding base will cause the pH to increase as it becomes more basic. And what we have to realize is, relative to adding a strong acid to just water, these buffers really do keep that pH in check as long as we don't add too much.
All right. So what is a buffer? So to make a buffer, we need a weak acid and the salt of its conjugate base. So you need to brush up on your conjugate acid-base pairs. And when we talk about having a conjugate acid-base pair, a lot of times we can write a hydrolysis reaction of any weak acid, right? So we need a weak acid in order to have a conjugate that's also weak, so that we can create an equilibrium here. So if we just have our acid in water, we're going to generate a small amount of its conjugate. But what we have to do for a buffer is to also add a significant amount of its conjugate, and we have to use a salt of its conjugate. So if it's an ionic compound, we have a conjugate base here, which is our acetate ion. We have acetic acid, CH3COOH, and we have this hydrolysis reaction written here. And our conjugate base is this acetate ion. So if we have, from our stock room, we have some sodium acetate or some other soluble acetate salt, we can add that to our acetic acid solution. And now we have, not only do we have quite a bit of our acetic acid, we also have our acetate ion. And that's really important for our buffer solution as we move forward and talk about how it works.
So what we like to do is write the acid hydrolysis for all of our buffer systems. And I'll show a couple more examples. And that's exactly what I've done here. I took the weak acid, in this case the acetic acid, and I just wrote the reaction with water, the hydrolysis reaction, and because it's a weak acid, it's going to donate the proton to the water, leaving us with this acetate ion. And we have our hydronium ion here. And the nice thing about writing the acid hydrolysis is you get this hydronium ion. So, we can get our pH from that hydronium ion. We're going to show you some tricks on how to do this, and some other ways we could do this as well. But just to be consistent, we like to write out the acid hydrolysis, and what it does is it shows you our conjugate pairs. So this is one of them, and here's the other one. So we have a weak acid and we have the conjugate base. That is a buffer solution. And I know you said this really clear, but I'm going to just repeat it. This is an ion here, and our conjugate base is an ion, and if we wanted to prepare this buffer, we would need an amount of this conjugate base, and we won't find it in the storeroom. We won't find a bottle of ions. What we will find are salts that contain that ion, and if we can choose a soluble salt, and the sodium salts are very soluble, and we dissolve it in water, we'll have those ions. Now, what about the sodium ion? Can you talk about that?
Well, sodium ion is a neutral ion, so it will not have an impact on our pH. So if you have sodium ions in water And if it were to react with water, it would produce sodium hydroxide. And we know that sodium hydroxide is a strong base, and strong bases will completely dissociate into their ions. So it would just go right back to its sodium ion. So in fact, sodium ion does not react with water and produce NaOH, and it's a neutral ion. So we can have as much of this in our solution as we want, and it will not affect our pH.
All right, so let's just look at a couple more examples and we'll do these really quick. Make sure you're getting this. I'm going to choose another weak acid. This time I'm going to choose HCN. This is a weak acid, and I want to start with the acid hydrolysis. So I'm going to write plus H2O, and this is my donatable proton from that weak acid. This will create an equilibrium where we have the Cn minus and H3O plus. The reason we do this is so that we can see our pairs, like our conjugate acid-base pairs. This is the two things we need for our buffer solution. They're on opposite sides of the arrows. And notice this is an ion. The conjugate base is an ion, so we would have to find maybe we would use NaCN, a sodium cyanide, to get those ions in water. And again, the sodium ion is just a neutral ion. Lastly, let's talk about a weak base. Because, we're saying we can make a buffer with a weak acid and its conjugate base. Well, we could also make a buffer with a weak base and its conjugate acid. So I'm going to just, why don't you talk about ammonia?
Yeah, so ammonia is one of these weak bases that you really should know if you're in general chemistry, working with buffers at all. Ammonia is something that we actually use quite a bit. It is a weak base, so when you put it into water, we have a hydrolysis reaction that produces the ammonium ion. So we have this ammonium ion, and if you have a salt, any ammonium salt that's soluble, you can use that as its conjugate to ammonia. Now, we often will write the acid hydrolysis even if it is a base that's reacting, because when we put the base in water, we're going to produce hydroxide ions in solution, and that's fine. We can do calculations with hydroxide and calculate how much hydroxide ion we have and still get to a pH, because as long as you have one corner of that pH square, if you have the hydroxide ion or hydronium ion or your pH or pOH, you can always go all the way around and get your pH. But for simplicity, we like to write the acid hydrolysis, and sometimes that's an ion, and that's okay. Sometimes both of your conjugates are ions, and we can give you an example of that as well.
Yeah, so we did choose the base here, but rather than write the base hydrolysis, which I did, but what we would prefer to do is actually write the hydrolysis, so the acid hydrolysis. So you might do the base hydrolysis just to identify your acid. And if you're having trouble with these conjugate pairs and trying to identify which is the acid and which is the base, really what you want to do is just count the hydrogens, because our acid is always going to have one more hydrogen than the base. So in this case, we've got the NH4 plus, we've got 4 hydrogens. The base, NH3, only has 3 hydrogens. So that's really kind of a pro tip if you're having trouble determining which one is the acid and which is the base. So we prefer to write the acid hydrolysis. That way we have our hydronium ion here, and it just keeps things consistent. So realize we are using a weak base here, and we would have to have a salt of the conjugate acid. So we'd have to have, now these ammonium salts are quite soluble, so it really wouldn't matter, anything with...
It's good to have a neutral. You'd want another neutral ion, so
yeah, maybe
NH4Br or NH4Cl.
Yeah.
Yeah.
Some other things to consider is cost. If you were looking at these salts, you might want to consider the cost. You wouldn't want a super expensive salt. And lastly, we just wanted to talk about when we have 2 ions, right?
Yes.
So let me just, I should have used the lasso here for my erasing. Now I'm so far in.
It's okay.
So what if we had like an H2PO4 minus, right? Now this could really act as an acid or a base, but if I'm going to have it act like an acid, if this is going to be my weak acid, I'm just going to write my acid hydrolysis. One of these hydrogens will go, we're going to have an equilibrium we're going to have HPO4 2- and our hydronium ion.
And this comes from when you have a polyprotic acid. So if you have something that can donate more than one hydrogen, like H3PO4, so if H3PO4 already donated one of its hydrogens away, we have this H2PO4-. And so we could have a salt of both of these mixed together. We could have NaH2PO4 mixed with, Na2HPO4. So we could have two salts mixed together that would also produce this buffer solution. One of them doesn't have to be neutral. We can have salts of both is the point.
Right. And in this case, we just chose the sodium salt. And again, that sodium ion is a neutral ion. So we are, we're not concerned with that affecting our pH of our buffer.
Right. So let's talk about how this works.
How do the buffers work? I'm going to start with a acetic acid again. It's a pretty common one. I'm just going to write the acid hydrolysis.
This is a good weak acid to know. This is a very common acid that we use in, in the real world, in buffer solutions. In laboratories, we use acetic acid buffers quite a bit, and it ends up being an example in these calculations as well.
So what we're trying to say here is, how does this work? Well, we said that a buffer resists changes in pH when a small amount of strong acid or strong base is added. So let's just say we're going to add HCl.
I want to point out that this buffer solution was not just this hydrolysis. We didn't just start with the acetic acid. We added also a salt of its conjugate. So we have some molarity of both of these, not just what came to equilibrium from the acid.
Yeah, really, the reason we're writing this acid hydrolysis is just to help us identify those pairs, the conjugate pairs, and that's a very good point. So I just threw some numbers that I made up in there. We would have to have amounts of both of these to have our buffer. So if we add HCl, what we need to realize here is acids react with bases. So we have to be able to identify which is the acid and which is the base. If we add HCl, that is going to react with the base. And look at this, single arrow, strong acid, right? We're going to produce a chloride ion, which is a neutral ion, and we're going to produce our acetic acid.
So we've reduced the amount of our base, we've reduced amount of our acetic acid, and what we've produced is our conjugate acid. But what we did was we eliminated and neutralized that strong acid. So the strong acid is gone, a little bit of your weak base is also gone, and you've produced a little bit of your weak acid. So we're back to the weak equilibrium, but we've completely neutralized that added HCl. And in this other reaction, if we've added base, if you add a strong base to this, it will react with the acid. And what happens? We have a single arrow. Both of those will go to completion, so that NaOH, that added NaOH, is gone. And we also reduce our weak acid by a little bit, and we increase our weak base. So as we've adjusted our equilibrium a little bit, but the added strong acid or strong base is completely neutralized, and that's how the buffer works.
Yeah, so if we went back to our original buffer system here with these molar quantities, we can see here that we were using up some of the base. So maybe this dropped to some amount smaller than 0.5. And on the other end, our acetic acid is going to increase by that same amount. And we're going to talk about this in the upcoming videos on this buffer series.
So please join us for these other buffer series videos, because we're going to walk through a lot of different types of calculations involving buffers, and it'll clear up all of the questions that you have regarding buffers. So we hope you join us for those.